I'm really sorry. I think we'll just start right away. So let's dive into the business. So we finished node 4 last week. Access control. So now I actually want to touch networking, maybe the rudimentary part of networking. Talk about it. How is AY? It's not funny. So, what is networking? Simply, a network is the interconnection of two or more devices, right, for the purpose of sharing information or resources. That's networking. In short term, interconnection of two or more devices with the purpose of sharing information or resources. So in this, module, we talk about, hardware part of networking, the software part, the protocols, and the encryption, right? So basically, we have two types of networks. We have more than two, but the most used, type is two, which is LAN and WAN. So we have PAN, we have MAN, we have CAM, a lot more, but the most used ones are LAN and WAN. So a local area network is a network typically spanning a single floor or building. This is commonly a limited geographical area, right? It covers only a short distance, right? Like this router, it's the LAN. Because immediately you actually, go downstairs. You see that the signal is not strong, or you will not see the SSID anymore. So that's a typical example of a LAN. It doesn't cover a large geographical area. But WAN, so is the term usually assigned to a long distance connections between geographically remote networks. So example of LAN is the internet. Yeah, because it covers a long distance or a large geographical distance. It's covers a city, states, country, almost everywhere. So that's typical example of a WAN, internet. So what are the network devices that we have? We have what is called a hub, right? So hubs are used to connect multiple devices in the network. Just think of a hub like your extension box, right? Where you plug your charger, your plasma, your anything into that extension box. So basically, that's how it functions. That's the function of hub, to actually connect multiple devices together. So they are less likely to be seen in business or corporate networks than in home networks. So mostly, even in homes, you might not actually see hub device anymore because it's been, outdated. Nobody uses it anymore, right? But even then, you will likely see it at home, not in corporate environments. So hubs are wired devices and are not as smart as switches or routers. So let's touch down on them. We have switch. So rather than using a hub, you might consider using a switch, or what is also known as an intelligent hub. Switches are wired devices that know the addresses of the device connected to them and route traffic to that port or device rather than transmitting to all devices. So basically, switch has, some little of intelligence built into them. They actually function like a hub too, because you connect devices to them as well, right? But, in a hub, whenever you are sending a message or traffic through a hub, all the connected devices to receive that traffic, even if the traffic is not meant for them. You get? So even if the traffic is not meant for them, they will still, take that, traffic. But switch, immediately you send a packet or a message, it only go to the owner, which is the device that that message is meant for, and not all other devices. So basically, that's the difference between two of them. So switch offer greater efficiency for traffic delivery and improving the overall throughput of data. So switches are smarter than hubs, but not as smart as routers. Switches can also create a separate broadcast domains when used to create VLANs, which will be discussed, later in the book. So let's talk about router too. So routers are used to control traffic flow on networks and are often used to connect a similar network and control traffic flow between them. So basically, say you have a hub, a switch, right? So this hub and switch, they are basically used within, a local area, maybe within your house or within a department or within a company. But immediately you actually want to do anything outside your company or outside your limited geographical area, you will need a router to route that traffic to the internet. So routers can be wired or wireless and can connect multiple switches. So routers can connect multiple switches. So smarter than hubs and switches, routers determine the most efficient route for that traffic to flow across the network. So now router has intelligence that is built into it that can determine the best route a packet or a traffic can actually travel to reach its destination, without any delay. Then we have a firewall. So basically, firewalls are used to, filter incoming or outgoing traffic, or inbound or and outbound traffic. Basically, that's it. It's basically used to filter traffic. So that's the function of a firewall. So a firewall is a network device used to filter traffic, like I said. It's typically deployed between a private network and the internet, but it can also be deployed between departments within an organization. So firewall filter traffic based on a defined set of rules, also called filters or access control lists. So firewall doesn't just work out of the box. You have to configure some rules. Is this net traffic permitted? Is it not permitted? When you see this traffic, are you going to block it or not? So you have to actually tell the firewall what to do. Right. But by default, firewall is going to block everything that is coming or going out of the network. So now you now sit and tell the firewall what to do, what to block and what to allow. So we have server. Server is a computer that provides information to other computers on the network. Just like, a client and a server, right? So server has some resources in it. Then you will go there to actually ask for that resources. So it provides information to other computers on the network. So some common servers are web servers, email servers, print servers, database servers, and file servers. So all those servers, they house one or two things, right? So all of these are by design, networked and accessed in some ways by a client computer, right? So servers are usually secured differently than workstations to protect the information they contain. So because server contains some sensitive information, information that is more important to an organization. So you actually want to put more security in that area or in the perimeter of the server than workstation, just like your computer or your phone, because they don't really have, some sensitive data in them. They have, but not as much as server does. Then endpoint. So endpoint is the ends of a network communication link, like your phone, your laptop, anything. Those are the endpoints. So our endpoint can be another server, desktop workstation. It can be a laptop, it can be a tablet, mobile phone, or any other end user device. So now, other networking terms that we have, aside from, the devices that we have on the networking, we have what is called internet. So Ethernet, IEEE 802.3, which is International Electronic Engineering, right? So basically, it's a standard that defines wired connection of network devices. So they are in charge of, a standard saying that all the vendor that is manufacturing a device has to follow this kind of wire, right? So that's why most of the time, Type-C will work for almost all the vendors. iPhone can use Type-C, Aptech can use Type-C, some systems can use Type-C, and that's because it has been stated that, by Ethernet IE 802.3 that, any device that has that port must work with a Type-C, mount. So this standard defines the way data is formatted over the wire to ensure disparate devices, that means, devices from different vendors can communicate over the same cables. So now device addresses. We have what we call media access control or media access control address, which is MAC address. So every network device is assigned a media access control, or what we called, hard-coded address, right? So this is an example. It's 00-13 like that. So that's a typical example of a MAC address. Almost all the devices has this MAC address. So the first 3 bytes, which is the 24 bytes, that means a byte has 8 bits, right? So the first 3 bytes, which is this, right, of the address denotes the vendor or manufacturer of the physical network interface. Dell has its own MAC address, HP has its own MAC address, iPhone has its own first 3 bytes MAC address. So mere seeing them, you can actually, tell that, okay, I think the vendor that actually made this, hardware is anyone, maybe Dell or HP, by just looking at the first 3 bits bytes of their MAC address. So no 2 devices can have the same MAC address in the same local network. Otherwise, an address conflict will occur. It's like me and you sharing the same IP address, and I'm trying to actually send a data to one of the IP. There will be a problem like that because they won't know which one to actually send the message to. Then we have internet protocol, which is IP address. While MAC addresses are generally assigned in an interface's firmware, IP hosts associate that address with a unique logical address. This logical IP address represents the address within the network and can be useful to maintain communication when a physical device is swiped with a new hardware. So basically, MAC address cannot be changed. There's nothing you can actually do to change MAC address. Or IP address, you can assign any IP address to any devices, anytime. Right. And this is an example of IP address. Right. The first one is what we call IP or IPv4, which is version 4 of IP address. 192.168.1.1. We still actually we map it out maybe today, how they actually arrive at this number. So, and the second one is IPv6, right? So that's how it looks like this. This is how IPv6 actually looks like. So this is a networking at a glance. So the diagram represents a small business network. The lines depict wired connection. Sorry, these are lines, right? So they depict wired connection. Notice how all devices behind the firewall connect via the network switch, and the firewall lies between the network switch and the internet. Don't forget that we say the function of a firewall is that it filters incoming and outgoing traffic, or inbound and outbound traffic. So majorly, it is mostly placed in between your router and the switch to actually filter the network, the traffic that is coming from the internet or the network that is going out from your network or from your organization. So this is the router that will carry the packets to the internet. And this is the firewall that will filter the packet or the traffic that is coming in or going out. And this is the switch that actually connects all the end devices or workstations. And this is the wireless access point, right? And this wireless access point, most of the time, is provided by the ISP, which is Internet Service Provider, mostly. So all these endpoints or workstations are connected wirelessly, right? So the network diagram below represents a typical home network Notice the primary difference between the home network and the business network is that the router, firewall, and network switch are often combined into one device supplied by your internet provider and shown here as the wireless access point. So if you see this as compared to this, here we have router, we have firewall, we have switch, all of them complete. But in this case, right, both the switch, the router, and the firewall are all being built inside these wireless access points. So your ISP or internet service provider, they will just give you these wireless access points and say, okay, place it anywhere, just like this. Then you can connect to the internet without, seeing switch or router or firewall. So this device has all of them embedded in it already. So it will do all those functions for you. But you cannot take this to, a corporate environment and be using it. So networking models. Many different models, architecture, and standard exist that provide ways to interconnect different hardware and software systems with each other for the purpose of sharing information, coordinating their activities, and accomplish joint or shared tasks. So computers and networks emerge from the integration of communication devices, storage devices, processing devices, security devices, input devices, output devices, operating system, software, services, data, and people. So that's where computer and network emerge from. So translating organization security needs into safe, reliable, and effective network systems. Start with a simple premise or idea. So the purpose of all communication is to exchange information, like we said, and ideas between people and organizations so that they can get work done, right? So those simple goals can be re-expressed in network and security terms, such as to provide reliable, managed communication between hosts and users, to isolate functions in layers, to use packets as the basis of communication, standardize routing, addressing, and control, allow layers beyond internetworking to add functionality, be vendor agnostic, scalable, and resilient. That's just in network in security terms. So basically what they are saying is they have to be reliable, they have to be safe, something like that. So we have this networking model. Well, I think you can remember this one. What's this? This. This is where is Alia? Where is Alia? I said you should understand this, like you should know this, this diagram. So that's the way it's Alia. Where is Alia? Yeah, we explain it now. So basically, OSILEA has 7 layers to it, right? And they are how internet works, how devices are connected, how data are being transferred on the internet. So the first 3 layers, which we call upper layer, are application layer. So they are application, presentation, session, we still explain them. Then the lower layer, which we call data transport. So they entail transport, network, data link, and physical. So those 7, you have to know them, know them. So in the most basic form, a network model has at least 2 layers in the most basic, which is the upper and the lower, right? So the lower layer is often referred to as the media or transport layer, and is responsible for receiving bits from a physical connection or wired connection and converting them into a frame, right? So frames are grouped into standardized sizes. Think of frames as a bucket and the bit as a water. If the buckets are sized similarly and the water is contained within the buckets, the data can be transported in a controlled manner. Raw data is added to the frames of the data to create packets In other words, a destination address is added to the buckets. Once the buckets are sorted and ready to go, the host layer takes over. You still understand, but basically, what they are saying is that, the physical layer, that's the layer we have wired, and how your wire are connected to all the devices. So the data link is where you actually add your packets. The network layer is where you input the IP address or the MAC address. So the transport layer is where you actually input your TCP or UDP, anyhow you want the communication to be transported. The session layer is where the session is established or cancelled. Presentation layer is where the formatting actually occurs to a format that you can actually understand, a layman language. Then application layer is where you interact with that data. So let's talk about that still. So now we have open systems interconnection. That's the full meaning of OSI model, open systems interconnection, which was developed to establish a common communication structure or standard for all computer systems. The actual OSI protocol was never widely adopted, but the theory behind the protocol, the OSI model, was really accepted. The OSI model serves as an abstract framework or theoretical model for how protocols should function in an ideal world or ideal hardware. Thus, the OSI model has become a common reference point against which all protocol can be compared. The OSI model divides networking tasks into 7 distinct layers. Each layer is responsible for performing specific tasks or operation with the goal of supporting data exchange. The layers are always numbered from bottom to up. That means you start from physical layer, which is layer 1. Starting from the top, that's layer 7. So the layer always numbered from bottom to up to top. They are referred to by either their name or their layer number. So you can just say, okay, application layer, or you say layer 7, or you can say network layer or layer 3. So you can actually name them anyhow you want. The conceptual layers are ordered and stacked to depict the flow of information from one device to another. As information traverses the model, each layer communicates directly with the layer above and below. So that means application communicates with presentation to network, network to transport to network to presentation, and like that, right? They all communicated. So the layers of the sending and receiving system correspond to the various states of information throughout the exchange. For example, layer 3 communicates with both the data link layer, which is layer 2, and transport layer, which is layer 4, and both systems leverage transport layer 4 for the same purpose. That means to carry the information from one system to another. The application layer, the presentation, and the sessions layer, which is from layer 5 to layer 7, right? We all know that application layer is in layer 7, presentation layer is layer 6, and the session layer is layer 5. So they are commonly referred to as data. However, each layer has the potential to perform encapsulation, right? So encapsulation is the addition of header and possibly a footer trailer data by a protocol used at the OSI layer. So you go to the application layer, you had the details. You go to presentation layer, you had the details of presentation, how you want the data to actually look like, how you want it to be formatted. Then you go to the physical layer, how you want the physical layer to be, to look like, you put it there. So basically that's encapsulation. You put all those information from layer 1 to layer 7. So encapsulation is particularly important when discussing transport, network, and data link layer. That's layer 2 to 4, which all generally includes some form of header. So at the physical layer, which is layer 1, the data unit is converted to binary. Binary is the language that computer actually understands, right? So from wired, from the signal, or from the electrical current coming from the wire, right? It will be converted to, binary, the language that the computer understands, which is 1 and 0s, and sent across physical wires, such as the Ethernet cable. So let's map some common networking terminology to the OSI model. An image file like a JPEG or PNG is at the presentation layer, right? Because you want, that image to look like JPEG or PNG and not PDF. That's where the formatting actually occurs, presentation layer. How you format the data is at the presentation layer. But logical ports, such as NetBIOS, are the session layer, right? Where you want to telnet, you want to SSH, you want to establish a communication between two devices or two remote devices. So that, of course, are the session layer. Where we have protocols like TCP, UDP, are the transport layer. How do you want that information to be transported? Is it through TCP, which is more secure, or UDP, which is less secure? Is TCP, which is slower, or UDP, which is faster? TCP they are under transport layer. Protocol, they are protocol under transport layer.
I mean, are they all OSI? They look like they are separate.
No, they are under OSI layer. OSI layer under transport layer. So basically, the full meaning of TCP is transmission control protocol. How you want your data to be transported. Is it through express or through sea or through land, like that? So if you want your information to be delivered faster from US, we basically use maybe an aeroplane or something like that to be faster. So that's where UDP comes, right? So you want it to be, slower, but it's sensitive and stuff like that. So you want to actually use C. So basically, the difference between them is that one is more secure than the other, and one is faster than the other. TCP is more secure, UDP is less secure. TCP is slower, UDP is faster.
Well, TCP works based on connection, I think it's connectionless, right?
Yes, it's connectionless. So routers sending packets happens at the network layer. That's where IP address comes in, where router comes in, where you actually connect to the internet. So switches, bridges, or wireless access points, sending frames are activities that occur at the data link layer, which is layer 2. Because that's where you deal with MAC addresses, right? So encapsulation occurs as data moves from the OSI model from application to physical. As data is encapsulated at each descending layer, the previous layer header, payload, and footer are all treated as the next layer payload. So the data unit size increases as it moves down the conceptual model and the content continues to encapsulate. Like the information keep adding up. Like for example, now a network layer, right? You want the header, right, to include the IP address you are sending the information to, which is the source address, which is your own laptop, and the destination address where the information is going to, or the data is going to, or the packet is going to, right? So in transport layer, you want to include either you want to use TCP or you want to use UDP. It has to contain that information. So and like that and like that. So we have TCP IP, which is transmission control protocol or internet protocol. The OSI model wasn't the first or only attempt to streamline network protocols or establish a common communication standard. In fact, the most widely used protocol today is TCP IP, and it was developed in the early 1970s. So the OSI model was not developed until the late 1970s. So the TCP IP protocol stack focuses on the core functions of the networking. So mere just looking like this diagram, what can you kind of like tell the difference between TCP IP and the OSI layer?
Yeah. It's still like translated information. But OSI, the OSI it includes maybe and OSI works with bare element transmission of information from the physical layer to application and just deploy the services of this TCP as a transport medium. The TCP works like focus on networking and what I mean by networking is just transmission of information like that.
Good points. But really, just look at it again. If you can see all the protocol that we have in TCP IP as compared to ASI layer, you know, one is 4, one is 7. In ASI layer, we have 7 layers from application to physical. But if you check the TCP IP protocol, now we're having 4. Sure you get. So now we have just application layer, we have just transport layer, internet layer, and network interface layer in TCP IP, as compared to ASI layer, where we have, you know, from application to presentation to network to session, like that. So instead of having application, presentation, and session, those 3, the first, you know, header, the first upper layer, so they've been kind of like merged into application layer alone. So you don't have the presentation and the session layer anymore. They've been actually integrated into application layer. You know, normally we should have like 7, but now we're having 4. Right? So the presentation and the session has been merged and is being inserted into application layer. So you don't need to kind of like, so when you are dealing with TCP IP, so basically they want you to mention 4 layers, not 7. When we are dealing with OSI layer, they want you to mention all the 7 layers. You get?
So does that make TCP IP faster than you like the entire process of OSI?
Yes, because now our network works today in today's world, we are using TCP IP. We don't use OSI layer anymore. But it's just that we cannot rule it out. They are like the foundation. But now we are using TCP IP protocol. But you have to know the two, both the OSI and the TCP IP. So here, application layer, it defines the protocol for the transport layer. Right? It defines the protocol for the transport layer. So the transport layer permits data to move among devices. Then internet layer, create or insert packets. You know, that's where we have our IP address and stuff. And network interface layer, how data moves through the network. You know, that's where we have our physical layer, you know, and the data link layer. Do we get it? So the most widely used protocol suite is TCP IP, right? But it's not just a single protocol. Rather, it is a protocol stack comprising dozens of individual protocols. So TCP IP is a platform independence protocol based on open standards. However, there is both a benefit and a drawback. TCP IP can be found in just about every available operating system, but it consumes a significant amount of resources and is relatively easy to hack into because it was designed for ease of use rather than for security. That means when they were designing this TCP IP, you know, we don't have hackers there. They just want everybody to connect and share data and share resources. So designing it, they don't really actually integrate security from the start. So it's not really secure. But they later make it secure, which we will talk about. So at the application layer, TCP IP protocol include telnet, file transfer protocol, simple mail transport protocol. So this is a protocol that actually deal with mail, anything that relates to mail. So DNS, you know, domain name service, anything that has to do with domain name, like www.google.com or www.yahoo.com. So the telnet is how you actually connect remotely to other device, right? By commands, telnet to your address or your system. So file transfer protocol. So it's a protocol that deals with how file is being stored, you know, transmitted, deleted, and stuff like that.
Is the FTP used?
No, it's because it's not secure.
Even FTP.
FTP2 is not secure. We have TFTP now.
For some systems,
But they are not secure. So that's why they are saying, there are still some system. You can actually force your system to use telnet or to use FTP. But basically, what they are saying is that they are not secure. So if you use them, you are using it at your own risk. Since you have a secure protocol, so why don't you use them? Instead of telnet, why don't you use SSH? So instead of FTP, why don't you use TFTP? Instead of SMTP, why don't you use SMTPS? It gets so like that. So the two primary transport layer, we still talk about the secure and non-secure protocol. So the two primary transport layer protocol of TCP/IP are TCP and UDP, which we've talked about. TCP is a full duplex connection-oriented protocol, whereas UDP is the simplest connectionless protocol. Can you remember that? We talked about it. Yeah. So basically, full duplex is like two-way communication. You can talk, I can talk. It's just like the road. One car is going like this, another one's going like this. But simplex is just a one-way communication protocol. The person can talk, or you cannot reply or respond like radio. You can't talk to radio, but you can only listen to what they are saying or what is coming out from the radio. So basically, that's just a simplex. It's a one-way communication. So in the internet layer, we have what we call ICMP, which is Internet Control Message Protocol, which is used to determine the health of a network or a specific link. ICMP is used by ping, traceroute, and other network management tools. The ping utility employs ICMP echo packets and bounce them off remote. So this is what we mean by ping. I think we should all know. So it's like ping. Is responding. So basically, this is an example of ICMP. So it's an internet control message protocol. It controls how packets, if your packet has an issue, it will tell you, like request timeout, right? So it will give you an error if there is any error in your means of communication, right? And if it is true, it will tell you, this is, connected, this is live. It's basically telling you that, okay, the device you are trying to kind of like reach is live. So, and time to leave is 112, like that. So we don't have to talk about this now. I just want to show you how ICMP works. So this is OSI layer, and this is TCP/IP protocol architecture. So you can see the OSI layer. We have 7 layers completed. We have the application layer, we have the presentation layer, we have the session layer, we have the transport layer, we have network layer, data link layer, physical layer. All the 7 layers are completed. But in TCP/IP, there are just 4. Basically, what they are telling you here is that this application presentation session layer, they've all been actually put inside this application layer. So the transport layer is this transport layer. The network layer is now called the internet layer. So instead of having the data link layer and the physical layer now, we are now having just link layer. Right. And these are the protocols. Right. We have FTP, we have TFTP, which is trivial file transfer protocol. We have telnet, we have simple mail transfer protocol, simple network management protocol, which is SNMP. We have NFS, we have LPD, X window, and this is the transport layer. Basically what they are saying is that all these protocols, they belong to this application layer, right? So this transport layer, the TCP UDP is the protocol under transport layer, right? I'm just tracing it like this, right? So the network layer or internet layer, that's why we have IGMP, basically IP address, then ICMP, Internet Control Message Protocol, like we said. Then under this link layer, that's where we have our Ethernet, like our MAC address. We have fast Ethernet, it's a type of cable. We have token link, we have FDDI. So I think we still talk more about them. Now, so let's talk about IP address. Like we said, we have two types of IP address. We have IPv4 and we have IPv6. So as a security practitioner, it is important to understand the basic components of Internet Protocol addressing, which is IP address. So the figure below shows the essential components of an IPv4 address, which will be covered in more details below. So this section will highlight some important historical aspects of IP, differentiate IPv4 and IPv6, and introduce the concept of public and private addressing. So at the end of this section, you should be able to determine if an address is IPv4 or IPv6, and if the address is public or private IP. So yeah, we have, this is a typical example of IPv4, right? Like 192.168.1.1, mostly we find it anywhere in our phone, our system has an IP address, our phone drew, almost all the gadgets that we have has an IP address. Even our IoTs, like our smartwatch, smart fridges, all of them, they have an IP address. And basically, this is how most of them looks like IPv4. So this is a typical example of IPv4. So how did they come about 192? I think we did this both in secondary school. That's good. Binary. Yes. I was about to ask. So it's binary, right? So binary actually has 8 bits. So binary basically has like 8 bits, like you have 1, 2, 4, 5, 6, 7, 8. And mostly when you are dealing with IP address, you count it from the left to your right. So the first one, the first bit has 128. The second bit is 64 divided by 2. The third bit is 32. Fourth bit is 16. 8, 4, 2, and 1. Making 8, right? 8 final. This is assuming that everything is 1 over here. This is like we have 1 on 1, 1, 1, 1, 1, 1. That means they are on, all of them are on. But also they can be off, they can be turned off. And in this case, that means we have all of them like this. That means they are off. Off. So when they are turned on, that means they will change to 1. When they are off, they are 0. So adding this together, right? 128 plus 64, 182 plus all of this is going to give you like 255. And if you add this together, it's going to give you 0. That's clear. That's clear, right? It is clear. If it's not clear, please, I can go back. Yeah. No, 256. No, it's 255. For now. So, how did they come about 182 in this case? Right. That means they actually added these two. This is on and this is on. Right. And this other one, they are off. So that means you are not going to add them together. So adding these first two together, that's like 128 plus 64. So that means you have 182. That's how they come about, or they came about 182. And as for the 168, the first bit is on. right? This is 168 is on, plus this is off, which is 64, right? The 32 bits is on. Then the 16 bits. No, sorry, the 16 bits is off, the 8 is on. So it's going to be 168. Is it 168? No. Yeah, 168. Yeah, 168. Yeah, 168. And this is just, all of these are off. And we have one on. So it's just one, just one. All of these two, they are off. We just have one limits. So basically, that's how you can actually make sense of any IP address that you see online. So it's not like it's coming from the heaven. So when you see any IP address like that, that's how you can actually add them together. So internet protocols are currently deployed and used worldwide in two major versions. Okay. You can't see. Like I don't get. Okay. Starting. Yes. Sorry. So internet protocol are currently deployed and used worldwide in two major versions. IPv4, which provides a 32-bit address space. So that means if you add all those 8 bits, like if you add them together, 8 plus 8 plus 8 plus 8, that's 32. Right? So that's where they come about. You know, IPv4 provides a 32-bit, address space because it is 8 bits in 4 different places. So adding it together is going to give 32. So which by the late 1980s was projected to be exhausted. So IPv6 was introduced in December 1995 and provides a 128-bit address space along with several other important features, which we will talk about. IP or host associate an address with a unique logical address. So an IPv4 address is expressed as 4 octets separated by dots. 4 octets separated by a dot. So where they came about the 4 octets is because it is 8 bits, right? Which is 8. So and they're all separated by dots. So you don't say 216.12.146.210 or 140. No, you say 216.12.146.140. That's how it is being called in a normal working environment. So each object may have a value from between 0 and 255. However, 0 is the network itself, so not a device on that network. So that means you cannot see an IP address, having 0, like 0.0.0.0. That's your IP address. No, can't. And 255 is generally reserved for broadcast purposes. So broadcast is from a single device to multiple devices. Like, for example, you want to ping a multiple device from a single device. That means you are broadcasting to them. Yeah. So each address is subdivided into 2 parts. We have the network number and the host number. So the network number is the number that actually belongs to a network. The host number is the one that has been assigned to you. So the network number is assigned by an external organization, such as the Internet Corporation for Assigned Names and Numbers. That's ICANN. Represents the organization network. The host represents the network interface within the network. Sorry, guys. I have to pick the call. It's important. Sorry. So, hold on, I'll just bring back 5 minutes. I'll call you back. Yeah. So. So to ease network admin, networks are typically divided into subnets. This is another bug entirely. But because subnets cannot be distinguished with the addressing scheme discussed so far, a separate mechanism, the subnet mask, is used to define the part of the address used for the subnet. So the mask is usually converted to decimal notation like this. You know, we said when everything is 1, right? We are going to add 255, adding them together. I'm saying they are all 32. That's like octets in 4 different places. So if you see the subnet mask like this is basically like /24, because this is 8 plus 8 plus 8, making 24. Right? So mostly it's written like this. That IP address may be 192.168.1.1/24. Basically, what they are saying is that these 3 false pockets actually belongs to a network address, and this last 0 belongs to a host. I hope you understand. You do. So the first 3 belongs to a network. That means you cannot actually use it. It's not for you. Right? It's not for you. And the 0 is a network. Is a host. That means that IP address actually belongs to you. So I don't know. Yeah, I'm assuming. Yeah, so keep my one. Then so me to the point around check it. Tell us if you take your money needs or drop. So with the ever-increasing number of computers and network devices, IPv4 does not provide enough addresses for our needs. So to overcome this shortcoming, because do I have to? Okay, we still talk about, don't let me just jump so that we understand. So to overcome this shortcoming, IPv4 was subdivided into public and private address ranges. Public means it could be used, anywhere. Private means, you cannot just see it on the internet anyhow. It basically belongs to a certain organization. So public addresses are limited with IPv4. However, private addresses can be shared by anyone, and it's highly likely that everyone on your street is using the same address scheme. So the nature of the addressing scheme established by IPv4 meant that network designers had to start thinking in terms of IP address reuse, because now IPv4 is now kind of like, it's not enough anymore, because this, where are we still? So mere just looking at IPv4, if you do 2 to the power of 32, right, it's going to give you like maybe 65 million plus or something like that. That is the total IPv4 address that we can have. So when they are kind of designing IPv4, they didn't know that there will be something like Internet of Things, and everything will be kind of like assigned IP address to. So currently, we've almost used IPv4 finish. So now they want to kind of like move to IPv6. So basically, that's how they come about IPv6. That before you finish IPv4, so let's come up with IPv6. So this table shows the private IPv4 addresses available for anyone to use. So if you see any address, right, from 10.0.0.0 to 10.255.255.254, right, that's basically class A IP address, right? So it could be used anywhere. Or if you see any IP address that starts with 172.16.0.0 to 172.31.254.255.254, that's a private IP address that belongs to a class B IP address. We'll still talk about them. And if you see any IP address that actually starts from 182.168.0.0 to 192.168.255.254, that's class C IP address, and it's a private IP address too. So the first octet of 127 is reserved for a computer loopback address.
The class C and class D IP address. They are not common. Yes.
The class C.
Yes.
The class C is the one that is common. It's the one that I often, if you check my IP address, it's going to be a class C on your phone or your system. I don't know.
But you didn't mention class because
because they are not widely used. They are basically reserved for one or two purposes, maybe for experimental or for research, stuff like that. So if I do, what's my IP address? Wow. So this is basically, class B IP address assigned to the system. Okay, because we are connected to router. But normally, if it's not connected to router, it's going to be a class C IP address. So this is basically pinging the ISP address, the people that actually ask, which is MTN, right? In this case. So that's the address that MTN actually give them to use with this router. So we said the first octet of 127 is reserved for a computer loopback address. You know what's a computer loopback address, right? You know the meaning of loopback. So loopback is basically like the troubleshooting IP address for your system. Like it's basically, for example, if you want to check if your network interface card has a problem, right? So you have to ping this IP address. If you can ping it, that means you don't have any problem. Basically, this IP address, this loopback IP address is basically used when you're trying to troubleshoot your system if it has a network problem. So to check if the network interface has a problem, something like that. That's one, right? So basically, it's a loopback IP address. It's up and running because there's nothing wrong with the network interface card. But if there's something wrong with the network interface card, the loopback IP address will not ping. It will not work. So basically, that's it. So the loopback address is used to provide a mechanism for self-diagnosis and troubleshooting at the machine level. So this mechanism allows a network administrator to treat a local machine as if it were a remote machine and ping the network interface to establish whether it's operational. Now let's check IPv6. We talked about IPv4. So this is IPv6. So IPv6 is a modernization of IPv4, which addressed several weaknesses in the IPv4 environment. So IPv6 has a much larger address field. So IPv6 address are 128 bits. We said for the IPv4 is 32 bits, right? So, but for IPv6 it's 128 bits. And to actually get the total number of IP address in either IPv4 or IPv6, you just do 2 to the power of the size. So in this case now, it's 2 to the power of 128. But for the IPv6, it's going to be 2 to the power of 32, which should be 65 1,656,000 and stuff like that. But for IPv6, you know, if you do 2 to the power of 128, you are going to get, is it billion or trillion? So, you know, it's going to take a while before you finish this kind of IP address. You can see that we have more address now. So, and as compared to IPv4, which is like 65 million, this is a billion already. So I don't think this century can actually finish it. Even, I don't know, if trees are converted to IoTs and grasses are converted to IoTs, we still have them remains. So also IPv6 has improved security. So the security was not built into IPv4, it's optional, it's not mandatory. But in IPv6, security is built into it, you know, by default. So IPsec or IP security is an optional part of IPv4 networks, but it is a mandatory component of IPv6 networks. So this will help ensure the integrity and confidentiality of IP packets and allow communication patterns to authenticate with each other. Also, in IPv6, we have what we call improved quality of service. So this will help services obtain an appropriate share of a network's bandwidth, right? So an IPv6 address is shown as 8 group of 4 digits. Instead of numeric 0 to 9 digits like IPv4, IPv6 addresses use the hexadecimal range, which start from 0 to F. Right? Like 0 to 9 and A to F. And are separated by colons rather than periods. No, IPv4 separated by periods. But now, IPv6 is separated by colon. So an example of IPv6 address is this: 2001:0DB8:0000:0000:FFF:0000, and like that. So that's how IPv6 address looks like. You know, it is more easier to kind of like memorize IPv4 than IPv6 because we still have more complicated IPv6 than this. This is just an example, but mostly you don't have to, you know, cram it or memorize it at all. So to make it easier for humans to read and type, it can be shortened by removing the leading zeros at the beginning of each field and substituting 2 colons for the longest consecutive 0 fields. So all fields must retain at least 1 digit, right? Even if they are all zeros, they must still retain 1 digit, maybe just 0, right? So all the leading zeros in this example now, we'll remove it and you will see. So after shortening the example address above, it's rendered as, you know, we still have 2001:0. The 0 now has been removed because it is a leading 0. So you remove it, right? And it remains DB8. Now we have 3 zeros that are consecutive, that follows, you know, one another. So you remove all of them by representing them with double colons. So that means if you have, you know, 5 leading zeros, you will remove them by adding double colons, right? So these 3 consecutive zeros has been removed and has been represented by double colons. Then we have FFF, nothing changes. So then we have leading zeros again. And don't forget, they said you must have at least 1 digit in that place. So now we remove 3 zeros and we leave 1 0. Then the next one, which is 0001, right? We just leave 1 there and remove the leading zeros. Is that clear? We don't in IPv6. So because mostly they don't have subnet mask. They do. Okay, we will still get it. Then we actually clarify it more. So as an IPv4, there are some addresses and ranges that are reserved for special uses. Don't forget that in IPv4, we say we have private IPv4, right? Also in IPv6, we have private IPv6. So if you see anything like :1, so that's the local loop back address, which is kind of like, relating to 127.0.0.1 that we have in IPv4, that we said is basically just used for troubleshooting purposes and for self-diagnosing. You can remember, right? So basically, that's what this :1 actually stands for in IPv6. And if you see anything that range from 2001, I am very sure the leading zero has been removed, DB8, then all the consecutive zeros has been removed. To this is reserved for documentation use, as an example of proof. And like that. So if you see anything like this to this, are address reserved for internal network use and are not routable on the internet. Not routable on the internet means that you don't normally see them on the internet. Maybe basically they are used for one or two reasons. There are some IP address that if you see them, you know that they are malicious. They don't just come online, except someone is using them to actually do one or two fraudulent things. So what is Wi-Fi? Which is what we call wireless fidelity. So fidelity. All right. Sorry. It's fidelity, like FIDELITY. So wireless networking, Wi-Fi. So it's a popular method of connecting corporate and home systems because of the ease of deployment and relatively low cost, right? So it has made networking more versatile than ever. So workstations and portable systems are no longer tied to a cable, but can roam freely within the signal range of the deployed wireless access points. So this is just the example of what we are talking about. However, with this freedom comes additional vulnerabilities. Wi-Fi range generally accommodates most homes or small offices. Range extenders or multiple access points may be placed strategically to extend the signal for larger areas, such as collegiate campus, like a college, right? So basically, what they are saying is that if you want this Wi-Fi to actually extend to this other compound, it's either you put an extender somewhere here, or you actually add another access point, maybe inside this compound too. There's one here. So okay, so downstairs. So that's basically in order to actually make it more, this. So Wi-Fi range generally accommodates most homes or office. I think we've talked about this. The Wi-Fi standard has evolved since inception. Typically, each iteration offers more throughput at faster speeds. To exploit a LAN, threat actors need to enter the physical space or immediate vicinity of the physical network, such as open ports at wall outlets or on a network device. So that's before, right? So when they want to kind of like maybe steal some sort of sensitive information in the network back then, so they will just come to like a data center and plug their their cable into an open port like this, right? Like this wallet, or they go to data center. They enter data center, right? Plug their cable into the switch or the router and connect it to their system to basically sniff, actually steal sensitive information that is being passed from one client to server, or from one client to another client, or from one server to another server. So, for example, given a physical access, threat actors may place sniffer tabs onto cables or plug in a rogue USB devices. Sorry. When you open smart, when you use what it says, yeah. So let's discuss. So sorry. Again. So, for example, given physical access, threat actors may place sniffer tabs onto cables and plug in a rogue USB device. So by contrast, wireless media offer threat actors opportunity, which do not require circumventing physical access controls. They can just, sit in this compound since the wireless, has an extender that they can actually connect to. Before they have to use cable, to see all the information that is going on. But now they can do that by just seeing this SSID or by just seeing this wireless connection being on. People can hack wireless devices like Wi-Fi like this. So that means they can just sit somewhere, like without actually entering the organization before hacking them. So they will just sit somewhere, tap into the SSID, connect to the Wi-Fi, then start hacking instead of coming to the data center with cable before.
But they have to see if there's a distance that you get to.
And it will not, but that's the more easier for them. They just have to move closer to where they can actually get the signal, as compared to you trying to break into that organization before. See you get. So it's more easier now to actually do that. So exploitation of Wi-Fi weaknesses or weakness can occur from outside the parameter of physical access control by capitalizing technological weaknesses or misconfiguration in that. Maybe they use a weak password or some hint that can actually make them connect to this Wi-Fi. And if they connect to the Wi-Fi, they can connect to the organization as well. So basically, this is how it looks like. This wireless access points. And it's connected to all these devices or workstations. So we have security of the network. So TCP/IP vulnerabilities are numerous. So improperly implemented TCP/IP stacks in various operating systems are vulnerable to various attacks, including denial of service attack, distributed denial of service attack, fragment attack, oversized packets attack, spoofing attack, and man-in-the-middle attacks. So these are all the attacks that can occur in a network environment. At least we understand some of them. So TCP/IP, as well as most protocol, is also subject to passive attack via monitoring or sniffing. Passive means that they don't have to kind of like physically present or interact with the system physically. That means they can do it outside your perimeter. So network monitoring or sniffing is the act of monitoring traffic patterns to obtain information about the network. That's a sniffing now. So you want to actually, steal some packets to see what they are, communicating. Maybe you can see some sensitive information in it. Maybe you can see password, username, and stuff like that.
What's the difference?
Which ones?
Sniping.
Sniping. Where's
I saw that
I actually don't understand this napping, sniffing, except I see the word. Okay, then we talk about this later. So observe the simplified network diagram below. Think about the various types of network traffic, web browsing, email, authentications, and alert traversing the BC information system highway. That is an organization network. Imagine if a threat actor was able to observe the traffic at various points on the diagram. What type of information might an adversary name? Say that an attacker placed him or herself in between the router and the firewall. That means all the traffic that you are being, taken from the internet coming to your, organization will be built, seen by an attacker, just placing him or herself in between this router and the firewall.
Yeah.
Before the person can be in the middle. It all depends. If the person is attacking from this point, from this router, coming from this router, the traffic has not hit this firewall already. So the attacker doesn't need to fight the firewall in this case. But if the attacker actually placed him or herself after this firewall, so that means the attacker has to, break through this firewall too and place him or herself between this firewall and the switch. So actually listen to the information being transferred. That's clear, right? Yeah, so that's how it is. So various network attacks that we have, like we said, we have denial of service or distributed denial of service attacks. So the prevention of authorized access to resource or the delaying of time critical operation, that's denial of service. You are denying, a service or people that have authorized access to that service from entering that service, right? So you actually overweigh or overwhelm the service by actually breaking it down. So then we have fragment attacks. In a fragment attack, an attacker fragments traffic in such a way that a system is unstable to put data packets back together. This is how information works. For example, say you have the information coming in 1, 2, 3, 4, 5, 6. They should be in an organized manner, right? So say the information is information itself, which is INFORMATION, right? So the attacker will now break that packet in such a way that it cannot be put together. Maybe they will just bring the M or N at the end, bring it to the front, and just do it like that. So now the network will be like, okay, let me just try to put it together. So during the process, they can just, the port is open now, trying to kind of like receive that information. So they will just use the opportunity. So we have oversized packet attacks. So purposely sending a network packet that is larger than expected or larger than can be handled by the receiving system, causing the receiving system to fail unexpectedly. That's clear. It's pretty straightforward. So it's because oversized, we are sending more packets than what a service can take or a device can take. Then we have spoofing attacks. Faking the sending address of a transmission to gain illegal entry into a secure system. Like saying, Aptech knows your system already because they are students and they assign some IP address to you, right? So anytime you are coming into Aptech, maybe from your home, you are remotely connected to Aptech, the control mechanism trusts your IP address because, it was Aptech that actually assigned that IP address for you. So an attacker coming in will be blocked because, the control mechanism will block that IP because the IP is not known to that control mechanism. So what the attacker will now do is that the attacker will now steal your IP address, right? So it will now tell the control mechanism that, okay, this IP address belongs to me because the control mechanism trusts that IP address. It will let it pass. Sure you get. So it's just manipulating people or IP address or MAC address or any identity to actually gain unauthorized access to a more secure.
Because I mean, just become like those, they are assigning the IP address by touch from another person. They are assigning it
to my own. Yes, yes. So the control mechanism is seeing that IP address because it has been told that you see this IP address, it is safe. Let him pass. Show you again. It's like a big organization whereby they don't know who is who, except maybe you are in the department. So maybe the security doesn't know that you are working somewhere because it's a very big firm. So they don't know who is who. So I stole your kind of like ID cards and I wear a suit and stuff like that. And went to security guard and be like, okay, this is my ID card. They will let me pass because I have the ID with me and all the details are there already. Maybe if they don't check the face very well, I mean, and there are some ID cards that they don't even use face. They are just like, like magnetized ID card that you can just swipe and you can just enter. So we have man-in-the-middle attacks. So an attack where adversary position themselves in between the user and the system so that they can intercept and alter data traveling between them. So an attacker placing him or herself in between you guys talking. It's like me sitting here and it's dropping everything you are saying. So I'm man in the middle. So in another cases, you sending, trying to kind of like maybe withdraw the money. So you are now telling the server that I want to withdraw 10,000. So a man in the middle, an attacker will just sit in between that communication, right? Maybe changing the address that the money is supposed to kind of like wire to his own or own address, or trying to actually purchase latest Bentley, and you input your address and stuff, and someone actually gets hold of that information. They can just change that your own address, your home address, to their own home address. So the motor or the Bentley will be delivered to their own home address because it has been changed by a man in the middle. So we have ports and protocols. So on a network, there are physical ports that you connect wires to. Just like if you turn that wireless access point at the back, you will see some ports you can plug RJ45 cable to if you check. So those are the first physical ports that you connect wires to. Those wires can be RJ45, any other type of cable. And logical ports. So, and we have logical ports. Those are the ports that we are mentioning the other time, like HTTP, HTTP, FTP, because they are dealing with number. They are logical. You cannot really see them, but they are ports. You have to connect to them. It's like you trying to connect to FTP. FTP is maybe port 21 or something. So you just say, I want to connect to this port 21. It's logical. It's not physical. Like the one you can just, take your cable and just plug and stuff like that. It works. So we have physical ports. Physical ports are the ports on the routers, switches, servers, computer, etc., to which you connect wires, e.g., the fiber optic cables. It's a type of wire that we have in networking. Cat5 cables to create a network. So it's like you, connecting your firewall, to this router physically using a cable, right? So basically, that's what they are saying. And we have logical ports. So when a communication connection is established between two systems, it is done using ports, right? So when you establish, like, you do SSH, or you do telnet to another system, so you use logical ports to actually do that. Because you are connecting to FTP without using wire, you are using a port because you will specify that I want to connect to telnet, which is port 21, right? Then the IP address. So basically, the connection is done using that logical port. So a logical port, also called a socket, is little more than an address number that both ends of the communication link agree to use when transferring data. Ports allow a single IP address to be able to support multiple simultaneous communication, each using a different port number. So in the application layer of the TCP/IP model, which includes the session, presentation, and application layer of the OSI model, reside numerous application or service-specific protocols. Data types are mapped using port numbers associated with services. For example, web traffic right? HTTP, which is port what? Port 80. So when you're connecting to the internet, you want to use that port, right? To actually connect to the internet, to the web. So then we have secure web traffic, which is HTTPS, which is port 443. So when you want to use 443, you will specify that I want to use this port 443 instead of port 80, which is not secure. So we have some well-known ports. And those well-known ports ranges from port 0 to 102423. That's a well-known port from 0 to 1023. So these ports are related to the common protocols that are the core of the transport control protocol, TCP or Internet Protocol model. So DNS service, simple mail, so all of them, they use this protocol because they are well-known. Then we have registered ports, which ranges from 1024 to 49151. So these ports are often associated with proprietary applications from vendors and developers, while they are officially approved by the Internet Assigned Numbers Authority. And in practice, many vendors simply implement a port of their choosing. Right? They will just say, okay, this is the port we want to actually use for this application. You know, maybe WhatsApp has its own port number. You know, that is no well known, but it's registered and it belongs to WhatsApp. Or Google has its own port number that just only belongs to them and stuff like that. And they'll be the ones to actually decide what port to actually use for what service or what application. So example includes remote authentication died in user service, radius authentication, which is used by Microsoft for authentication mechanism. So we have Microsoft SQL Server, which uses 1433 or 1434, and the Docker REST API, which uses this port. So they are just registered ports. It's not well-known ports. They are registered by a particular or specific vendors to use for their own service. So then we have dynamic or private ports, which ranges from 49152 to 65535. So whenever a service is requested that is associated with well-known or registered ports, these services will respond with a dynamic port that is used for that session and then release it immediately. So it is like just borrowing that port. So immediately that service is closed, the port will be taken again. So that means another person can use it anytime they want to use it. So now let's talk about secure ports. Some network protocols transmit information in clear text. That means in the plain text that you can see and make sense of. Meaning it is not encrypted and should not be used. So clear text information is subject to a network sniffing, right? So this tactics uses software to inspect packets of data as they travel across the network and extract text such as usernames and passwords. So network sniffing will also review the content of documents and other files if they are sent via insecure protocols. So the table below shows some of the insecure protocols along with recommendation secure alternatives. So that means instead of using port 21, which is FTP, try to use port 22, which is secure file transfer protocol. That's the secure alternative for the FTP, which is not secure. Port 23 is not secure, which is used for telnets, for remote connection, right? So instead of using 23, why don't you use 22, which is SSH, which is a secure shell? So we have port 25, which is not secure, which is SMTP, Simple Mail Transfer Protocol. But we now have port 587, which is SMTP built on top of TLS, which is Transport Layer Security. Yeah, we'll still talk about them. So, and it all goes like that. We have time, which is not secure, DNS, which is not secure, and port 853 is more secure, which is DNS over TLS. We have HTTP, port 80, which is not secure. Instead, use 443, HTTPS, which is more secure. We have 143, which is IMAP, Internet Message Access Protocol. So instead of using this port 143, use 993, which is IMAP, and like that, and like that. It all goes like that. So basically, they just explain their function, like file transfer protocol sends the username and password using plain text from the client to the server. So this could be intercepted by an attacker and later used to retrieve confidential information from the server. So this secure alternative, which is SFTP on port 22, uses encryption to protect the user credentials and packets of data being transferred. It's just that one is being transported in plain text and another one is now using encryption. Time of 6:23. So, and like that. So we said port 23 is not secure, which is telnet. So basically, telnet is used by many Linux systems and many other systems as a basic text-based terminal. Like you want to remotely connect to another device. So you want to use telnet, which is not secure. So instead of it, use SSH, which actually use encryption to actually connect to a remote system. And we have port 25 SMTP, which is basically used for sending and receiving emails, which is not secure. It doesn't use encryption. And port 587 for SMTP over TLS, which actually uses encryption and like that. So we have three-way handshake, right? How you actually interact with a client, you interact with server, right? So this is how it works. So between the client and the server, there is a system for synchronizing and acknowledging any request. So it is known as a three-way handshake. This handshake is used to establish a TCP connection between two devices. And this is how it works. To establish communication on the web server, the client sends synchronization packet to the web server, port 80 or 43. It's like you trying to kind of like, download a movie on the internet. And for example, YouTube. And you want to know if the YouTube is actually ready to kind of like make the transaction, right? Then you will send the same message, basically asking, YouTube server, how far are you live? Are you there? Then the YouTube server will kind of like send both the message that you sent in the first place, which is a send message, and acknowledge message that's okay, I'm there, I'm live. What do you want? Back to the client in this case, right? So this is a request to establish a connection. The web server replies to the same packet with acknowledgement known as a send ACK, right? That I'm live. I saw what you sent to me. I'm live. What do you want? Finally, the client acknowledges the connection with an acknowledgement. At this point, the basic connection is established and the client and host will further negotiate secure communication over that connection. So then if YouTube has the video you want to download, to send it to you, or you guys agreed on what ports to basically use to actually make the transaction. That's all about that. So tomorrow we should move to understanding network, cyber threats and attacks. So we'll talk about this tomorrow. Yeah, we should talk about it tomorrow. I don't know. Maybe we can actually, we shall talk about it tomorrow. So, shut down off the jump. No worry. I got this.
Thank you. Yes.
Yeah, it should be done before tomorrow, sir, because like we are about to maybe mouse so you might kilo direction, but yes, then I'll have to respond. Yeah, I will before today or tomorrow. That's it.
I'll just maybe when I come tomorrow.
Okay, thank you. Don't move on, keep me outside. But I